started looking at different types of materials based on their conductivities. The Gershberg are that model. And we have seen that we can easily explain what metals are. So we have these allowed and forbidden bands of energies, and if you have your Fermi level to lie within an allowed band, then you get a metal. If it is in between, you have seen that it's an insulator, semiconductor, or semiconductor based on the width of this gap. And we have seen why in intrinsic semiconductors the Fermi level lies exactly halfway between conduction band and valence band. Then we said, well, let's focus on semiconductors. And we looked at a bunch of different properties of semiconductors. And most significantly, we have seen that there are two types of semiconductors based on how these bands, conduction and valence band, are aligned in K-space. If there is this difference in K-space, then this would be an indirect gap, otherwise direct. And we have seen certain examples to that kind of semiconductors. Then we looked at ways of electrical conduction in these materials, and we have seen that at finite temperatures, when heat is greater than 0 Kelvin, we have seen that the Fermi distribution may become greater than 1, significantly greater than 0 in the conduction band, which increases binding probability of finding electrons in the conduction band. But this comes from valence band, and we have seen that in intrinsic semiconductors, if you have electrons here, then you have absence of electrons in the valence band, which will act as positively charged carriers, electrons. Okay, they will behave as if they are positrons. So then you have the electric field. Electrons will move in one direction while we move in the other direction. Then we said, okay, this is nice, but based on how these bands are shaped, based on the curvature of the bands at the edge of at the minimum or maximum of these bands, that you will get an effective mass for electrons and holes, which will affect certain stuff like conductivity, because it affects mobility of electrons and holes, and certain other parameters. So we call this as an effective mass. And it's a way to capture interaction in all of the interactions that holes and electrons go under into a mass term. So they act as if they're under influence of a unified force. Okay. So, any questions so far? So this is just a brief overview of what we have done in the last week. Now, we'll change gears a little, and this is nice, but it is boring. Because there's nothing interesting here in terms of conductivity. So last time we started with this. Rather than having a pure semiconductor, let's think about silicon, for instance. Each silicon atom in lattice has 4 neighbors. Okay, so I'm just drawing it in plain fashion. Okay. Now, rather than having a perfect crystal, let's put a phosphor atom here. Now, what happens in this case? These guys, they share electrons, and these ion cores are very well shielded by those electrons. But when you add a phosphor impurity into the crystal, what happens? Here you share 4 electrons and they're perfectly balanced, but now you have 1 extra electron coming from this impurity atom. And then, since this is not perfectly shielded anymore, there's an ion core there. And we said, well, this electron is going to be in the vicinity of this impurity atom, right? And then we said, well, this looks like a hydrogen atom, right? There is a positive charge coming from proton, there's an electron orbiting around this thing. But of course, there are things different now. We cannot treat this as a free electron. It's going to have some effective mass. Also, there is a dielectric environment, so we cannot use epsilon 0 anymore. It's not in free space. Then, we said, okay, for hydrogen atom, I had my EH to be minus 13.6 eV, and this purely comes from these constants, right? So you have 2, 4, 5, epsilon 0, h bar squared. So if I replace this and this with the values in silicon, then I can find the energy that this creates in this material. So this ED, we named it ED because it donates 1 electron to the crystal. So this is the donor. Okay. So we get something like this, 13.6 eV times that here. Effective mass of the electron divided by actual mass of the electron, and then we have E squared, epsilon squared. So electrons, this now this is relative. Okay, and if you do the calculation for silicon, you get something like 20 millielectron volts. Okay, and the actual observed value is a little higher than this. It's about 30 millielectron volts. So what happens here is when you include this donor atom impurity, now you have an energy state. This is again my Fermi level. Now you have this single state that comes from the impurity. That's about 30 millielectron volts above the Fermi level. So, if you put enough of these together, then these orbits will start overlapping. Actually, we have value. I should have a value for the value, but you can actually calculate the size of this orbit. And if you have enough impurity atoms, it doesn't have to be too much, you'll see that they may overlap and form impurity bands. Now, that's one type. Now, the other type that I can do is acceptor. Okay. Rather than giving an electron to the crystal, may lack that electron and take it from the crystal. This time let's put a boron atom. Okay. So this time we'll have the opposite. Basically, to be able to bind with these silicon atoms, it's going to take one more electron that it can take. So it's going to be negatively charged effectively. But in the vicinity, this will leave a hole behind. So we'll get essentially the same thing, but this time it's like a reverse hydrogen atom. Okay. And same logic goes there as well. Now you can talk about the acceptor, and it's going to be similar to that. Okay, I made a mistake here. So this is not from Fermi level. This is actually like you're closer to the conduction band. This is 30 electrons. So this is from the conduction band. This is going to be from valence band. I don't know the effective mass, but it's going to be similar to this. Okay. It's not from Fermi level. That's impurity level, energy level is going to be from conduction band or valence band. So if it is an acceptor, that will be closer to the valence band. Our calculation will be from conduction band. Okay. So, if you have enough of these impurities, in this case you'll have excess electrons, almost free electrons in excess. Let's say you have a few of these scattered around. And if you have overlaps of these orbits, now you can picture this in this way. Now, you're dumping electrons into the system, which will result in shift in the Fermi level, because this is your vacuum level, and if you have more and more electrons, what happens? The probability of filling the conduction band should increase. So Fermi level shifts upwards, and this will increase the probability of finding electrons in the conduction. Or if it's an acceptor state, its effect is going to be the opposite, because now you're capturing free electrons. So this Fermi level will move down, and then it's going to be something like this. But now you will create holes in the valence band. Okay. So in one case, you create excess electrons. In the other case, you create excess holes. So this, in general, is called a P-type semiconductors, where the dominant carrier, charge carrier, holes, where you have excess electrons, and this is N-type. Okay. Any questions?
When you're putting the effective mass for the acceptor system, are we going to put the effective mass of hole? Or?
Yeah, of course. Right? Good.
Here we consider as a hydrogen atom, and yes, we put one electron
So,
pretty much.
Here you have your free particle as electron. So that's what moves in the crystal. Here you have hole as your free particle, if you like. So you need to use the effective mass of hole. Good question.
They are the same, yes?
No.
Hole and
No.
electron.
Actually, we discussed this in a previous lecture that you may have very different effective mass of electrons in the conduction band and effective mass of hole. They don't
No,
matter.
in the same, for example, in the valence band, they are the same for electron and hole mass.
Oh, now, of course, because in valence band, actually what we're dealing with is electrons, right? What's actually filling the empty state that's next to it is electron itself. And as we discussed, as electron makes this motion, it looks like rather than dealing with a sea of electrons, we focus on a single hole. So yes, I mean, you may talk about effective mass of electrons, going to be the same thing as effective mass of hole in valence band, but here we are dealing with free electrons, which is in the conduction. They are not the same.
And the mobility also is different.
Yeah.
So can we say that's why we have positive Hall effect coefficient in some cases? The mobility-
Yes, I mean, if majority of carriers are holes, then yes, that's the reason exactly. Okay. So we looked at that as well, and that explains the majority of charge carriers may be holes, and since they are positively charged, they act as if they are positively charged. You may have positive hole coefficients. Any other questions? Yes.
Did you consider lattice and electron and this, like there is a distortion and extra atom is
We don't consider it.
for energy like measurement
Yes.
we have to
In an actual treatment, you need to consider that. But as you can see, the measured value and the calculated value, there's a actually considerable difference. So probably that's coming from many things like distortion of the crystal and factors that you don't take into account here. But again, what matters here is the idea and its overall effect on the energy balance and the changes that it causes on the electronic properties of the semiconductors. We are not trying to solve the system like in its full glory and its full detail. Rather, we are interested in the overall effect. Okay? And the overall effect is going to be creation of these states and also shift to a further level because we're talking about electrons periodic structure. And then we use block function, block theorem, to show that there are actual formational bands. But in amorphous structures, that assumption breaks apart. You don't have a periodic structure. So this band picture doesn't apply. It requires a completely different treatment of quantum mechanics to those type of materials. Okay, so you cannot apply the ideas that you get from normal solids. Anything else? All right. So now, this is where things will start getting interesting, because now we can start making functional devices using these, because now we sort of created an imbalance. We distort the equilibrium. So the first thing that I want to talk about is the is thermoelectric effects. In N-type and P-type semiconductors. So let's say you have a piece of semiconductor at temperature T. Okay? And then the current density for electrons, this is the current density for electrons, and written like this. Then the electric field. Not the vector can be extended to 3 dimensions. Okay. And then maybe I should use, since this also has a negative sign within, I should do it this way. So E. And I can do the same thing for holes. So P, mu, H, and E. So now let me use P for consistency. Let's use P for density of holes. So these guys are density of electrons or holes. And then you have the same charge, but since this is also positive, we'll get the same thing. So let's leave this one. Okay, so this is current density for holes. Okay. Now, if I look at the energy carried by an electron in a hole, that will be something like this. So this is the energy carried by a unit charge. So the expression is something like this. Is going to be EC minus mu divided by E. That would be an overall minus sign. And then plus 3 halves kBT that comes from the thermal energy of the electrons. And I need to divide this by E as well. Okay, and then EH is going to be mu minus EV again divided by about it, that makes sense, right? Electrons in the conduction net are going to have this much energy plus thermal there, and in the conduction net they're going to have this much energy plus thermal there. Now, what do I do with this? Let's say I have this as well. Let's say I have a slab of material. One side is hot, the other side is cold. And because of the energy carried by these electrons, when you have temperature to be high, and on this side the temperature to be lower, there will be a charge imbalance based on, of course, material properties. And this charge imbalance will result in a thermal, actually its origin is thermal, of course, electric field. And the expression is something like this. So this is a constant of material called the Seebeck coefficient. Okay, and this T is the gradient of temperature. Okay, so this, we have different temperatures of size of the material. This will form a temperature gradient within the material. And based on the Seebeck coefficient, there will be an internal electric field because you have different number of charges within the material. This holds true for any type of material. It can be metal or semiconductor. I don't know if insulators have high Seebeck coefficients, or probably not. But you can find metals or semiconductors that have fairly large Seebeck coefficients. And with this, we can actually create potential differences on the order of hundreds of millivolts. Okay. Now, what is this connection with this stuff? Let's say I do something like this. Let's say I have two materials, two semiconductors. One of them is N-type, the other is P-type. And then I connect these two together from one side, and from the other side, this thing is connected to a battery. Okay. And then let's put a switch. When I close the switch, what will happen? Here, my majority of carriers are electrons, right? As soon as I complete the circuit, my electrons will start flowing in this direction. Here, majority of carriers are holes. What happens when I close the switch? Which direction do they move? What? So down, right? Towards the negative terminal. Now what do you see here? All of my charge carriers are moving from one side to the other. So they must have certain energy that they can carry. So they must take heat from this side and deliver it to the other side. Okay? And the this is written by the rate of change of heat is going to be basically the energy carried by this stuff. So I'm going to write this as E plus I B times the electric current that goes through the circuit. Oh, sorry, this is H. I've written B because if I call this material A and this material B, now you see that actually this is not just because we are not constantly electrons, because we have electrons here moving and holes here moving, but what matters is the net energy carried within this material. So what we do is I'll label this as IA, and also I think this should be a minus sign, although in my notes is a plus sign. It should be a minus sign because the sign of the charge carriers are opposite, so the net effect has to be difference between these two, and multiplied by the current, the total current that goes through the circuit. So the amount of heat that is transferred from one side to the other in a given time is given by that expression. It's a parameter of how much electrons and holes within this material can carry the energy that they have. Do you know what this thing is called? Yeah, so this is a Peltier plate. Now, what's interesting about this thing? Can you see? You're taking heat from one side and delivering it to the other. Thermodynamics. What does it mean? So I'm going to create temperature gradient because I'm extracting heat from here and delivering it to the other side. So eventually what happens is temperature on this side is lowered while temperature on the other side increases. And this is very commonly used actually in modern electronics, although it's not perfectly efficient. What you do is you extract heat from here by air cooling or water cooling, and this side actually can really lower its temperature, because what happens if you increase temperature of this side a lot, then these guys also have thermal conductivity, so that that heat will be transferred back to the upper stage, so eventually the whole thing will warm up. But if you extract heat from the other side, you can leave this side at lower temperatures. Indeed, if you use stages of Peltier plates and so on, you can, I don't know, but you can routinely go down to minus 100 Celsius. It's commonly used, it's everywhere. If you use the Raman spectrometer downstairs, it uses Peltier plates to cool the CCD down. In my lab, we have Peltier plates to heat samples or cool samples. So this is just a one simple application of P-type and N-type semiconductor materials. And typical materials that are used in these Peltier plates are, I've never worked with these, but this is selenite and this is telluride. So they have high Z coefficients. Any questions? Yes, please.
For solving the temperature gradient, you use electrons, but as far as I know, phonons are responsible for carrying the thermal properties.
Well, there's two components. One, yes, you're right. there will be a crystal part of the thermal component, but 2, there will be an electronic part. So if you look at the total heat capacity of the material, this consists of 2 parts, a crystal and electrodes. Okay? So here you're considering the electronic effect. And indeed, actually, my explanation about this overall thing heating up is related to that. You're not taking thermal conductivity of the crystals here because they don't matter that much. But if you don't extract heat from this side, eventually these materials will start transferring heat from one side to the other. Remember, we started in equilibrium. There were no temperature gradients to begin with. But as soon as I start passing this current, as soon as I close the switch, heat from one side will be transferred to the other. Of course, there will be collisions with the crystal and so on, and you'll generate heat because of this current, which will be the phonon part of this thermal picture. But again, overall effect of that part is going to be heating the whole thing up. But if you extract heat from one side, the stuffer part, what I'm saying is you can cool this side down. You don't have to take that into account because we start from thermal equilibrium. Is this clear?
Not that much. I didn't get the term you're talking about. There is no lattice term there.
Well, we don't have to include that because you're not interested
Because
in
they're
that.
saying that like thermal properties are like exactly phonons, and
No,
there was a theory about that.
That's missing.
Maybe.
Yes, I can show you from here actually. There are 2 components of thermal properties. One comes from the electrons and the other comes from the crystal cells. So let me show you from here. Yeah, 156. So, which class is this one? Where did you see that?
In my undergraduate, they were saying that at first they assume that electrons are responsible for thermal, but like if that is the case, so we have other materials that they don't have free electrons,
So
but they
for metals you have 3 electrons, and for semiconductors you have almost 3 electrons, and then they can carry heat. But that cannot be solely responsible for all thermal properties of materials. So that's the beginning point. For metals, the more dominant part is the electronic contribution. For insulators, it's the crystal part. Okay? So that information that you have is not complete. Is it clear? So there are, yes, 2 components for thermal properties of materials. Yes, there's phonon contribution and there's electronic contribution. Here we don't have to consider the phonon contribution at this stage because we start with thermal equilibrium. We are not interested in what crystal does in here. Okay? We are not creating a thermal inequilibrium and then driving these charges. We're driving charges and trying to see its net effect. Okay? Question?
Yes, I want to know the order of current or voltage for increasing ambient temperature.
It's about several amperes, like 2 amperes or something. And typical, now the power dissipation is like 10 watts or something like that. But of course, it depends on the size of the thing that you're trying to cool down. And typically, the CCDs that you cool is this big. They're very small, but you need something on the order of 10 watts. Maybe even less. Okay. Anything else? Yes.
I don't understand why calculators have very
parts of others?
I think the main reason is these materials are not perfect conductors, which means a lot of collisions. And yes, you can also, there's electronic contribution here and hole contribution here. So you are actually doing a lot of excess work other than that you're trying to do. You're driving other charges. Also, as this one side warms up, you start cooling the other side. Sorry, you start warming the other side because now these materials will start conducting heat to the other plate. So you're also starting to, trying to deliver that heat back down here. So that lowers efficiency. Compared to other methods, I'm not 100% sure. There are several other methods that we can use instead, but I'm not sure why they're that efficient. Is it okay for an answer? The actual thing is you're trying to do a lot of work against thermal conductivity of the material and driving other charge carriers, whether in opposite direction. They also carry. You got an answer back? Correct. Anything else? No? All right, now, that's the first simplest application of this. Now let's start asking more complicated questions. What happens? Let's say I have a metal. Okay. And I have a doped semiconductor. Okay. So this is an N-type semiconductor. What happens if I bring them together? I have a piece of metal, I have a piece of semiconductor, and I want to bring them together. What will happen to these bands? How they will connect with the bands of the metal? Now, to be able to answer this question, first we need to look at what the work function is. We briefly mentioned what that is, but let's take a look at it in more detail. Now, bringing these two materials together means that we need to take a look at these surfaces closely. And at the edges, you're going to have something like this. Now, let me draw from here. This vacuum, or this outer region, far away from the surfaces and influence of anything else, is going to be at zero potential. So this is my vacuum level. I define it to be at zero potential. Okay? And here, my Fermi level lies here. Here, Fermi level is different. And this difference, basically, is called the work function. It's a measure of how much energy it will take to remove one electron into vacuum. Okay? So it's a measure of the energy needed to take one electron to the vacuum. So let me write this down. Energy required to remove an electron to vacuum. Just outside the surface. And typically we are talking about, this is very crude, but tens of nanometers, okay? They would completely get rid of any surface effects. We're talking about tens of nanometers, and the better material can deal with something like that. So, this work function is basically this one. This is my work function. And then I have further level. Now, work function is the property of material. It is different from metal to metal. For instance, you can have two isolated metals. Since their chemical compositions are different, this mu's are going to be different, but our vacuum is here and it's defined as 0. So you may have different work functions for these different materials. Okay. Now, before going into that question, what happens if I bring these two metals together? If I combine these two metals, what will happen? You guys know. So, how is that going to happen? So what you're seeing is, I'll get a new Fermi level, like this. So throughout this material, I'm going to have the same Fermi level. And what is the physical reason for this? Why that happens?
Wasn't it something like there would be two different levels, and if we use voltage, we can bring...
Well, forget about voltage. What am I looking at here? These are energy levels, right? These are energy bands. And the reason why I drove them at different heights is because they have different energies. So what happens? When I bring them together. What's that? Sorry,
Nothing will
well, are you sure you have electrons here with high energies, and you have lots of free available states here with lower energies? Yeah, so you have lots of electrons here, and they want to minimize their energies, and you have available states when you bring these two things together. So there will be a flow of electrons from one metal to the other until you get an equilibrium. Okay? So there will be flow of electrons. These electrons will start filling up these empty states till you get an equilibrium between these two metals. Okay? And this actually has very interesting consequences. Because now, yes, there are lots of free electrons and so on. But if you simply bring two metals together, do not allow them to connect with anything else, this side will start having excess electrons, and the other side will have excess positive charges. This thing called contact potential difference. And actually, it's a very important technique in atomic force microscopy. We use this in AFMs to measure certain quantities related to materials. And when we start talking about AFMs, I'll go into details of this thing. But for now, I want you to think about this. When I put two metals together with different work functions, it's not just going to sit there, actually. There will be electrons flowing one side to the other, and there will be charge imbalance. And it's not something that you can measure with your voltmeters, because as soon as you hook up your voltmeters, you're going to create an electric ball that will neutralize this thing. You won't be able to measure that. Rather, you need to use capacitive techniques to be able to measure this effect. You cannot harvest charges from this thing. Okay? We'll talk more about this, especially in the AFM part, but on Friday we'll bring these metals and semiconductors together, and we'll see that actually we'll make a functional device out of this thing. It's going to give us very nice results. Any questions before we finish? I would like to remind you that you need to submit your first reports for the project by 5:30 today. Hard copy or no, it doesn't have to be. Anyway, there are homeworks you can pick up. Yeah.
Bastır verin dediniz. Yalnız burada değil, ben bilmiyorum. Ben verdim, gösterme istiyormuş, o da ilgili atar dedi. Hoş geldin. Bizi öyle seviyor. Ses kaynakları. Dikkat et, ses kaynakları.
Font 9, it is like 14. Doesn't matter. It's numbers for overall public. And that format.
It's living. I covered it very
Atlas'ı kısaltmamız gerekecek. Sonucu da referanslar
Şu soruyu soracağım. Bu ileride... Hayır, bakmayacağım. Hadi bisiklet.
نه باور میکنم میگونی واسه بهتر یعنی منظور نه من هم راحت یا سخت جواب تو سوال اصلا
من دیگه خیال راحت شدیم
آره بهتره ما
تکرار مثلا قضیه
آره آره بعد اصول من بود اون یکی هم جدوله هم
Я как-то не разбиралась какая. То есть это как платье выглядит.
Клиент там платье, рубашка, платье. Сарафан.
من اینجا